For decades, the computer industry relied on a simple formula for speed: make the central processor's clock tick faster. Those early, bulky desktop machines relied on CPUs executing instructions in a single serial line. But by the early 2000s, this approach hit a physical wall. You can only shrink transistors and push clock frequencies so far before the silicon generates too much heat to function. The era of the single, ultra-fast core had peaked. To keep scaling, engineers built horizontally. Instead of one fast core, they turned to graphics processing units, GPUs, and later machine learning-specific tensor processing units, or TPUs. These chips process thousands of tasks at exactly the same time. While they share this parallel philosophy, their internal layouts differ. TPUs use a few massive, specialized units designed strictly for multiplying huge matrices. GPUs pack hundreds of smaller, highly flexible streaming multiprocessors into a single chip. Modern artificial intelligence doesn't rely on a single, blazing fast brain. It requires an orchestra of thousands of compute units working in unison across a massive grid. This chart tracks computational performance versus data transfer speeds. While GPU math capability has exploded upward, memory bandwidth has barely crept up. When a processor finishes math before memory supplies the next numbers, cores sit idle. That widening gap is the memory wall. Scaling an AI model effectively means mastering physical logistics. Success depends on the speed of data lanes as much as the logic of the code. Navigating this bottleneck requires perfect synchronization between the data and the silicon. Way out on the edges is the global memory, or DRAM, massive but slow. Far closer, built directly into the processor blocks, is shared memory, or SRAM. It is blazing fast, but space is strictly limited. Even if the data arrives on time, developers must ensure the cores don't waste the effort. That starts with Rule 1, avoiding if-else logic. In a parallel system, all threads must execute the same instruction at once. If code hits a conditional branch, half the chip sits idle while the other works. Every idle core is a wasted trip to memory. The second trick is shrinking the numbers themselves. By dropping the precision from a highly detailed 32-bit format down to 8-bit, engineers literally halve the physical weight of the data, allowing twice as much information to travel across the board in the same amount of time. Next is operator fusion. Instead of computing a single math operation, sending the intermediate result all the way back to slow memory, and retrieving it again for the next step, the code is written to perform the entire sequence of calculations at once, while the data is still inside the processor. The fourth technique is a paradox: throwing work away. Because reading and writing to distant memory is so costly, it is actually faster to permanently delete intermediate variables during training and recalculate them entirely from scratch when you need them later. You don't usually think about geography when you write code, but here, the goal of the software is strictly spatial. Trap the specific numbers in the absolute fastest, closest areas of the silicon for as long as possible. Global memory reads data in physical burst blocks, not individual numbers. To retrieve efficiently, requests must be grouped contiguously. If the data's shape misaligns with these windows, engineers inject blank zeros, padding the matrices so they snap perfectly into those hardware boundaries. The final trick is tiling. Rather than processing a giant matrix all at once, developers chop the data into highly specific subblocks. These tiles are sized specifically to max out the tiny capacity of the fast shared memory. The chip loads a tile, runs every possible calculation it can on those specific numbers locally, and only then ships the finished piece to slow memory to grab the next block. The math operations aren't divided based on algebraic rules. They are sliced up based strictly on the exact microscopic square footage physically available on the silicon chip. All these physical constraints came to a head with large language models. The algorithm that stopped these giant models from crashing GPUs is called FlashAttention. Earlier attention mechanisms failed at scale because they generated massive intermediate matrices and continuously wrote them back and forth to slow global memory, completely clogging the transfer lanes. FlashAttention bypassed this by aggressively tiling the input data and fusing the operations. It forces the hardware to keep the pieces on the fast part of the chip. This diagram shows the key to the algorithm, the online softmax. Instead of waiting to load the entire grid to calculate the probabilities, FlashAttention computes a running tally, updating the totals block by block. The math never has to leave the local cache. FlashAttention revolutionized AI through the realization that, at extreme scale, software is effectively a hardware logistics problem. Developing the next generation of AI forces a departure from abstract equations. It requires a deep physical sympathy for the silicon itself. But understanding the theory is only the first step. To really grasp these mechanics, you have to build things yourself. If you're ready to start writing your own models from scratch, check out the Learn by Doing with Steven YouTube channel. You'll find practical tutorials that put these exact concepts into action. And for deeper conversations on where this technology is heading next, listen to the Steven Data Talk podcast, available on YouTube Music, Spotify, and anywhere else you get your podcasts. You can find all the links in the description below.